Now, next, what I'll do is I will give you two more flavors because we have already discussed the underlying algorithms, and because we've discussed the underlying algorithm, let me just give you two flavors quickly. The first flavor is what is called as the cooperative neuro-evolution. So we discussed cooperative coevolution, and so let's see if neuro-evolution is a valid problem for cooperative evolution or not. So let's do this. So eventually what I need to do, eventually I need a neural network which will have neurons like this and not drawing all the connections, so just drawing some lines over here. My encoding is for each and every neuron. So I say a neural network is nothing but a collection of neurons, or my genotype became something like this, a variable number of neurons. So this was neuron 1, neuron 2, neuron 3. Now, if you understand why do we need a hidden layer in a neural network, why can't I just have the input to output layer? So the input to output layer without the hidden layer can solve only linear problems. It can solve only linear problems. So what the hidden layer does is it reprojects the input space into a new high dimensional space such that the new space is linearly separable and can be solved directly, and each one of them are what are called as the latent features of the new space. So the hidden layer ultimately transforms the nonlinear input space to a latent feature space such that the problem is linearly solvable. So every neuron tries to find good latent feature. So every neuron tries to find out a good latent feature. Now, good features are something which are independent of everything. So you can actually use statistical measure to find out the goodness of a feature. So good latent features are the ones which help convert a nonlinear problem into a linear problem, and some statistical measure could be used to find out how good it is. So I can say that I can independently find 1, 2, 3, 4, 5 independent features. I'll independently find 5 independent features, and therefore I can say this is species 1, this is species 2, and this is species K. So every species is a neuron, but then of course the problem is not independent, the problem is cooperative, because if I find out 5 great features independently, they can come as 5 independent features. So what I need to do is find out first feature. To find out the second feature which is good, it helps linearly solve the problem as well as it is different from feature 1. I find out feature 3 which is good and different from feature 1 and 2. And sometimes the best feature 1 may not actually in an iterative manner give me the best other features. So I need to calculate features who are individually good, and each feature solves a part of the problem which none of the other features can solve. So they are independent features. And therefore, I can, without saying any further, have the same master-slave architecture where K is a variable size of a variable number of species and solve it up. Now I'll use another trick over here, that these are the same problems, unlike previously where x1, x2 was a different problem than x3, x4. Every species is solving the same problem. So I say every species is solving the same problem, and the problem of finding good latent features. And therefore, instead of maintaining k species, I can just maintain one species. So instead of saying this is species 1, so instead of saying this is species 1, this is species 2, this is species 3, this is species 4, what I can do is I can just say that because they're all solving exactly the same problem, I just take in one species. So I just take only one species. So this is neuron 1, this is neuron 2, this is neuron 3, and so on. So n individuals, just one species where each one of them is a neuron. So again, if I need to do cooperative coevolution, let me find out what is the size of, what is the fitness value of this. So fitness, I mean again same thing, fitness, ranking, scaling, crossover, mutation appears to be pretty normal. Making the new individual appears to be pretty normal. So let's calculate the fitness value of this. So let's say the fitness of neuron I. Now remember that a neuron does not have a fitness, a neural network has a fitness, a species does not have a fitness, the ecosystem has a fitness, a part of gene does not have a fitness, the entire genomic sequence has a fitness. So there's no fitness of a neural network or species, there's no fitness of a neuron or a species, there is a fitness of the entire neural network, or there is a fitness of the ecosystem. So I cannot calculate fitness of just a neuron I can calculate fitness of an entire neural network. And therefore what I do is the same theory of representative, the same theory of the representative. So I take in k neural networks. So these are all the neural networks of variable sizes. So these are the k best neural networks. So I take any one of them, let's say this one. So now I've already explained, so I can go extremely fast. You know what am I doing? So that's the same neural network of this one. And what do? I just replace this neuron in as one of the neurons over here. Let's say as a convention, I do it at the first one. So it's the same neuron. And the first neuron is replaced by this one. I do it for all of them, I take the average fitness, and that's the one that I get. So that's fitness value by substitution. That's a fitness value by substitution. So I maintain k best neural networks. The best neural networks are by calculating the fitness value. I'll be creating many neural networks. So I just take the best few of them. I store it up explicitly as representative. Whenever I see a better one, I store it up as a better representative, and I take the best k neural networks, I substitute the first one by my individual. If it's better than this neuron, then its fitness will improve. and I should be able to look at it and calculate the fitness value, and I take the average over all such k best neural networks, exactly same as before, and that's the fitness value of this one here. What I can also do is I can calculate fitness by sampling, so that's method 1. So this is using representatives. So what I can also do is I say method 2 using sampling. So I take this neural network, I take this neuron k times, and I create random neural network by sampling other neurons, sometimes small size, sometimes large size. Sometimes small size, sometimes very large size. So the first neuron is fixed to my individual over here, whose fitness needs to be calculated. So I call it as random ANN1, random ANN2, random ANNK. So first neuron is fixed and the others are randomly sampled, and take the average fitness or the average loss. Here you don't need to maintain in ranks, so you get the fitness value, you get the loss value. So that's another way you can calculate the fitness value. Now what I'll also do is to extend it into a master-slave architecture. So let's say this is my slave, all the different neurons. This is what we just discussed. So this is slave solved by using co-evolution. I also have my master. So the population is basically neurons, which is the kind of combinatorial. This time it's not strictly combinatorial optimization problem because the sizes are different. So this is what is a ANN. So the first is small number of neurons, the second one is large number of neurons, the next one is small number of neurons, very small number of neurons, very large number of neurons, and each one of these is basically a pointer to some population over here. It's a pointer to some neurons over here. So similarly for others. So a neural network is nothing but a collection of neurons. So it means this neuron, this neuron, this neuron, this neuron, this neuron. Okay, why are they pointing to the same neuron? But anyway, so this neuron, and this neuron. So 3 neurons. So let's do one. I mean, and both these evolutions happen in parallel. So first what I'll do is, let's discuss the master first. So I'll make this neural network, calculate the loss value, rank them up, calculate the expectation values, do selection crossover, do mutation. The mutation will be structural, add neurons, structural, delete neurons, or parametric, change it from this to this. For these networks over here, I'll take in individual over here. I'll take in the rank 1, rank 2, rank 3, all the way up to rank K from the master. So these are best K neural networks from master population. And then I'll just replace the first neuron with the one that I have over here and look at the difference. So the average of this is my fitness. And then of course I can also do is for every neuron, just look at which all neural network is it a part of and take the average fitness value. So that is same as before. So this neuron in all the neural networks that it's a part of, find out the k-best neural network that it's a part of and take the average fitness. So that way also you can get in the fitness function value, same as before. So the only interesting thing is instead of multiple species, there's just one species because every neuron, it solves exactly the same problem. And because every neuron solves in exactly the same problem, I've got one species in the population pool